Okay, so I want to explore a little bit how we can have elements of different orders in the same group. Oh, yes. And I have my assistant with me here. So I'm going to pick a group that's actually somewhat familiar. So this is a nice abelian group. We can add things in whatever order we want. I'm going to call this the circle group. And as a set, I'm just thinking about the interval from 0, including 0, up to 2 pi, but not including 2 pi. The operation I'm going to use here is angle addition, right? So anytime we do trigonometry, geometry stuff, we say things like, oh, well, we wrap around at 2 pi radians to make a full circle. So 3 pi radians would be the same as pi radians. And the collection of all possible angle measurements on a circle does form a group. And we can add angles just the same as we would add real numbers. There's just this extra consideration when we wrap around. So I can still say things like 1 radian plus 1 radian equals 2 radians, and I get slightly strange behavior that pi radians plus pi radians gives me 0 radians. But I expect that you've seen stuff like this before. We just didn't have the name group for it yet. Okay, so here's a concrete problem for us to consider. Classify all elements in the circle group who have order 4 or less, and which of these have order exactly 4. So I'm looking at angle measures between 0 and 2 pi radians, and I want their order to be less than or equal to 4. If I go off my definition, then n copies of my angle x have to add up together to give me 0 radians. And n has to be less than or equal to 4. So I'm going to use a bit of a trick and say that adding angles together is the same as just taking n copies of x, adding them up, and checking to see whether this is an integer multiple of 2 times pi, right? I go around by x radians. I do that n times. Was this, in fact, exactly k times around the circle, where I know that 1 time around the circle is 2 pi radians? So if I take this equation is in terms of real numbers, so I can just say that my x has to be equal to k divided by n times 2 pi, and my denominator n has to be less equal to 4. I can go a little bit further than that and say that since x is supposed to be strictly less than 2 pi, k, my numerator, has to be less than n. So I can just list out all of the x's, all of the angles, whose order is 4 or less. So my x is k on n times 2 pi. N is 4 or less, so those have got to be 1 on 1, 1 on 2, 1 on 3, 2 on 3, 1 on 4. 2 on 4 is really the same as 1 on 2, so I've got that one covered. And 3 on 4. Those are my choices for k on n. And I could also say x equals to 0 times 2 pi, right? Those would be my total list of possibilities. For the second part of this question, which of those angle measures has order exactly 4? I'm checking that 4 is the smallest multiple of x to give me 0. I can't have 3x equals 0. I can't have 2x equals 0. I can't have x equals 0. And again, this is all as angles. So I can't have this be equal to 0 or any multiple of 2 pi. So since I have my list, right, I have the list of all the possible k on n, I can just check all of these fractions, and what I get is, well, 1 on 1 times 2 pi has order 1, right? Because that's already 0. 1 on 2 times 2 pi has order 2, and so on. So the only two fractions that give me what I want are 1/4 and 3/4. So the angles which have order exactly 4, there are 2 of them. There's pi on 4 and 3 pi on 4. So out of the whole circle group, which consists of infinitely many different measures of angles, only 2 of them have order equal to 4. As a follow-up to this, do all the elements of the circle group have finite order? If you give me any angle you want, I'll call it x. Oh, do you have an x? Do you have an x for me? Oh, I don't think Octavia has an x for me. That's too bad. Can I take any angle x, add it to itself some finite number of times, and get back to 0? Because we're just going on a circle, right? Eventually we'd have to get back to 0. But I claim that is not the case. So I'm going to look at a particular angle measure, and I'm going to look at the angle of 1 radian. So a little bit less than 1/6 of a circle. I know what the multiples of 1 are going to be, right? 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5, and so on. I get all of the positive integers. Can I ever have a positive integer that is also a multiple of 2 pi? No, I can't. Pi is an irrational number. I cannot represent pi as a fraction, right? If I had, say, 3 equals 2 pi, that would mean that pi is the same as 3/2, but it's not. Pi is irrational. So I have this sequence, I'll say, this family of angles. They are all different from each other, and they will never get back to exactly 0 radians. So we're in the case that no matter how many 1s I add together, I will never get back to the identity element of this group, which is 0. So I have to say that the order of 1 is infinity. So the circle group has some elements that are of finite order and some elements that are infinite order. And they all just sit in there and play along together pretty nicely. We're going to see that finite groups are a little bit nicer to work with than infinite groups, right? We've been spending the whole term looking at different systems of modular arithmetic, and all of those are finite groups. When we're in the case that we don't have a finite group, if we have a group with infinitely many different elements, we can still get a little bit close by trying to find a way to write out all of those different elements. So this will bring us in the direction of the generators of a group, and that'll probably be discussion for next Thursday's lecture. So That is the end of lecture for today. You should have all the tools you need for this week's tutorial. If there's any questions in that, please leave me a question in the discussion section on our Moodle website. And make sure that you have your submission for the midterm exam submitted by Friday this evening, May 1st. All right, I will see you later.